Moving on with equation of motion for a system of particles. We're now ready to extend the equation of motion to include a system of particles that are isolated within an enclosed region in space, as can be seen on the screen. Let's focus our attention on the particle I, this one. As we can see, there are two forces that act on that particle, the small fi and the capital Fi. The small fi is the resultant force of all the other forces from the rest of the particles that are exerted on that particle. That is the resultant force. While the Fi is the resultant force also, but these are the effects of forces that are outside of this region, and this includes electrical, magnetic, or contact forces. Altogether, they constitute the Fi, the resultant net force outside of this region. So in order to apply for the equation of motion, let's first isolate the object and draw an FBD diagram. So this is the net external force that acts on that particle. This is the net internal force that acts on the particle. This is the FBD. And if we draw the kinetic diagram, this would be the MIA I. And of course, these two graphics are equivalent. So applying the equation of motion from sum of F equals to MA, this would result to, since we have two forces, Fi plus, small fi is equals to MIA I. So this is the equation of motion for that particle. But when this equation of motion is applied to each or to the rest of the particles, similar equations can be obtained. And if all these equations are added together vectorially, then we obtain a more general form of equation, which is the sum of all external forces and the sum of all the internal forces that act on all of the particles is equal to the sum of Mi and the product of Mi and Ai. Now, if we're going to evaluate this expression, which is this net internal forces, this is equal to 0 because the force that exists between any two particles occur in equal but opposite. Therefore, the internal forces between any two particles equates to 0. Remember the law of gravitational attraction between any two particles. There is the same force, there is a mutual force that acts on both bodies, but since we are considering the net force between the two particles, then the net is 0 because they are equal and opposite. To illustrate another example, consider an object that is hung at the ceiling with an applied force at the bottom, P. If we want to analyze what is the effect of action force P on any arbitrary cross-section area, then we would do an FBD of that partial body to expose any internal force that is present in that cross-sectional area. And by doing so, we should apply the application of force along Y, summation of force along Z, summation of force along X, and static condition states that there is or there must be a net zero force. So by visual inspection, without doing this, we can actually see that there must be a force that is equal and opposite to that of P. This is the internal reaction force to that external applied force P. So we see that the effect of P is tension on this body. So P is an internal, and it is equal and opposite to that of action P. So this is similar to that of the case of law of gravitation, and this also is similar to the phenomenon of this rigid body or a system of particles. So the sum or the effect, the total effect of those internal forces between any two particles is equal to 0. Therefore, our final equation is Fi is equals to MIAI. Now, let's concentrate our attention on this distance, RG. It is a position vector which locates the center of mass G, the center of mass G of the particles. Now, what is the center of mass? Let's review what is the center of mass. In statistical language, the center of mass can be thought of as a mass weighted average position. Okay, that is a precise definition of the center of mass from the point of view of statistics. It is a mass weighted average position. To explain or describe further what does it mean, or what does that statement mean, I'll have to draw something, a series of mass on a given axis. Let's say we have these masses aligned on a given axis, and we're going to find the location from which all particles have zero relative mass weighted position. So in order to find for Rx, the formula is you have to multiply the mass of one object or particle times its distance x, and the mass of the other particle times its distance, and you would do that to the rest of the particles, and then divide that all together by the total masses. So that is why it is called mass weighted average, because you have mass as weight, which means not a force but a factor, because you're not just averaging the individual position of each particle, but you are factoring in the individual mass as well. That's why it is called mass weighted average position from point of view of statistics. Additionally, the center of mass is the point to which the force may be applied to cause a linear acceleration without angular acceleration. It is a point. It is a hypothetical point in a given body wherein you can apply a force which may cause a linear acceleration but without angular acceleration. And the last definition that is also important is that center of mass is the particle equivalent particle equivalent of a given object for application of Newton's law of motion. It is a particle equivalent of a given object. Now, let's go back our discussion on this position vector Rg. We'll have to erase so that we have more space. So let's go back our attention with the position Rg, as we have already defined what is the center of mass. We have mRg is equals to the sum of mi/ri. Instead of using x, y, we use r to describe the position of all the particles. And m, of course, is the total mass, which is the sum of all the individual particles. Now, assuming there are no particles entering or leaving the system, differentiating this equation twice would result to MAG equals to the sum of MIAI. And substituting this into this would result to F is equals to MAG. Therefore, the net force that acts on the system of particles is equals to the total mass of the system of particles times the acceleration of its center of mass. And since in reality, for a particle to have a mass, it must have a finite size. Therefore, this justifies the application for bodies that can be represented as a particle.